This soup of electronic waste might look like a dump, but it's actually, quite literally, a gold mine. A ton of circuit boards like these can contain 40 to 800 times more gold and 30 to 40 times more copper than can be mined from their natural ore. So that begs the question, what are we doing still digging up the earth, whilst electronics end up in landfill or incinerators? Current electronic waste recycling methods have been held back by big limitations, but that might be about to change. Scientists have recently developed a new way to reuse key metals using microorganisms like bacteria and fungi. Bioleaching, as it is termed, has the potential to be less environmentally damaging, more effective, and significantly cheaper than currently available techniques. And companies like Bioscope, who will feature later in this video, are already developing this technology at industrial scale. So what makes bioleaching such a compelling solution? And what needs to happen for it to become widespread? I'm Luke, and you're watching The Upshift. In 2022, the world produced 62 million metric tons of electronic waste, or e-waste. And with a yearly expansion rate of 3 to 5%, it's one of the fastest growing solid waste streams. E-waste produced in high-income countries is also frequently exported to lower-income countries where law enforcement on its disposal may be less stringent. Dumping e-waste, as you can probably imagine, doesn't do the environment much good. E-waste appearing in landfill sites can cause problems as rainwater filters through it, dissolving toxic metals and chemicals, carrying them into the surrounding soil, groundwater and surface water. It can also lead to toxicants entering the food chain. Alternatively, the burning of e-waste releases toxic chemicals into the atmosphere, also not ideal. Aside from the environmental harm caused by e-waste, discarding rare earth and other critical metals, despite their scarcity, seems wasteful at best and reckless at worst. It's no secret that the energy transition faces a resource challenge. According to the Royal Society of Chemistry, around 347,000 tonnes of copper will be needed in the UK by 2030, just to build wind turbines and solar panels. Rarer critical metals such as lithium, cobalt, indium, gallium and nickel are essential for core supporting technologies ranging from EV batteries to semiconductors. Now there is some debate about when, and in fact whether, the geological reserves of some of these metals might be exhausted. But even if global supply is sufficient, it's by no means equally distributed. And so both local and geopolitical tensions may limit access to this supply. To name a few examples, the Democratic Republic of Congo, facing insurgency, has large deposits of cobalt, copper and tantalum. Russia, amid geopolitical tensions, holds vast lithium reserves crucial for battery production. And Taliban-controlled Afghanistan contains significant rare earth elements and tin deposits. All in all, it's hard to imagine an increasingly digitised and electrified society that doesn't draw on recycled electronics to meet supply. Besides being inefficient and environmentally damaging, a traditional take-make-waste model simply won't be able to match future demand. The question remains then, how do we recycle it? It's kind of difficult to explain the benefits of bioleaching without first talking about the traditional recycling methods. The two most common ones are known as pyrometallurgy and hydrometallurgy. Pyrometallurgy usually consists of the following two processes. Roasting is the process of heating an ore in the presence of oxygen, but not to the point of melting. This converts metal sulfides and other compounds into oxides, and simultaneously removes volatile impurities. Smelting, the second process, then takes these metal oxides and reduces them to the metal using a reducing agent like carbon. The metal forms in melted liquid form at the bottom, whilst carbon dioxide is given off as a gas. As you might guess then, this method isn't ideal. It's energy intensive, costly, and comes with high emissions, including carbon dioxide from the reduction reaction and toxic gases from burning plastics and other chemicals found in electronic waste. Hydrometallurgy, on the other hand, uses aqueous solutions for the recovery of metals. The core step in hydrometallurgy is leaching. This involves dissolving the metals from recycled material into solution, typically using acids or bases. You might infer from the name that this method shares similarities with bioleaching, which we'll come on to later. Dissolved metals can be recovered from solution using various methods. These include adding chemicals to form precipitates, using electrolysis to plate pure metal onto electrodes, or through cementation, where a more reactive metal displaces and precipitates the target metal. The perks of hydrometallurgy include its ability to selectively extract specific metals, a lower environmental footprint compared to pyrometallurgy, and flexibility in handling different types of materials. That being said though, hydrometallurgy isn't without its own drawbacks either. It often involves hazardous chemicals, uses a large amount of water, and produces liquid waste that can be challenging to treat and manage. One thing we haven't really spoken about is that a lot of this recycling doesn't actually happen in the country where the waste is produced. A large proportion of e-waste produced in the UK, for example, is shipped overseas, to Europe and other countries like Japan, China and India. This is because high-income nations often face high disposal costs and more stringent environmental regulations, and so exporting waste represents an economic loophole. The issue is, though, that in many of these low and middle-income countries that receive the waste, recycling often happens through informal, unregulated methods. Workers use unsafe techniques like incineration, toxic acid treatment, or, in the worst case, open burning, leading to serious environmental and health risks. And this is why bioleaching is changing the game. It's a recycling method that's environmentally favourable, low energy, and surprisingly affordable. So much so, it's already catching the attention of major tech companies, who have voiced plans to build plants for their own use. So how does it work? Bioleaching uses naturally occurring microorganisms like bacteria and fungi to extract metals from their ores or electronic waste, and can occur through several different mechanisms. But much like hydrometallurgy, what bioleaching really boils down to is converting metals into a form that's soluble in water, such that they can be extracted from all the plastics and other materials found in e-waste. The key difference with bioleaching is that the acids and other metals typically added in hydrometallurgy are actually produced by the microbes themselves, as natural byproducts of their metabolism. So let's say we've got a pile of e-waste. First, it's crushed into a fine powder to increase the surface area for the chemicals to act. The powder is subsequently placed into a bioreactor or leaching vessel containing a solution of microbes and all the nutrients for them to survive. Now, there are three common mechanisms through which bioleaching microbes dissolve the metal ions into solution, and often multiple mechanisms take place simultaneously. Acidolysis is the name for the process where acid-producing microbes like fungi and bacteria break down metals using organic acids. As they feed on sugars like glucose, they release acids which react with metals and metal compounds to dissolve them into solution. Acidolysis is a common and effective way to extract metals like lead, nickel, zinc, and copper. One example of a microbe that uses this mechanism is Penicillium simplicissime, a species from the same genus as Alexander Fleming's penicillin-producing fungus. This fungus helps leach aluminium and nickel by producing gluconic and oxalic acids. Another key bioleaching mechanism is complexolysis. Whilst acidolysis relies on acids to break down metal compounds, complexolysis uses molecules called ligands or coalescing agents secreted by microbes. These ligands bind to metal ions, forming stable soluble complexes that pull metals into solution. This process not only extracts metals, but also protects the microbes themselves by detoxifying harmful ions. Complexolysis is the mechanism used, for example, by cyanide-producing bacteria to leach gold and silver. Unlike industrial cyanide, which is toxic and persistent, biologically produced cyanide is generated in lower amounts and degrades more easily, reducing environmental impacts. Complexolysis is especially effective for extracting transition metals like gold, platinum, and palladium thanks to their ability to form complexes with these microbial ligands. The third bioleaching mechanism is known as redoxolysis. This occurs in microbes called chemolithotrophs that oxidize metal ions to gain energy, for example by oxidizing iron 2+ ions to iron 3+. The iron 3 then oxidizes target metals, causing them to lose electrons and dissolve into solution, whilst each iron 3 gains an electron to regenerate iron 2. These microbes can also oxidize sulfur to sulfuric acid, linking redoxolysis to acidolysis. This process is effective for extracting metals like lead, nickel, zinc, and copper. As I said, bioleaching may occur through one or more of these mechanisms, and the primary mechanism depends on both the microorganism used and the metal that needs to be recovered. After metal ions are dissolved in solution, they can be extracted using similar methods to those I described for hydrometallurgy. For recycling methods using bioleaching, the choice of bacteria is extremely important. Different types of bacteria and fungi will show different capabilities of leaching different types of metals. A bacteria that achieves 100% yield of indium, for example, might achieve a very poor yield of strontium, whilst a different type of bacteria might show the complete opposite trend. The conditions of the medium where the microbes are grown also plays a crucial role in bioleaching efficiency and metal recovery yields. That's why thorough research in this area is essential to identify the most effective microbes and optimize the process. But success in the lab doesn't always translate to successful commercial-scale operations. Controlling environmental factors on an industrial scale is much more challenging. A big challenge is finding robust microbial species that can thrive in harsh, metal-rich and acidic environments that also produce effective bioleaching agents. This is the reason why bacteria naturally found in mines are often used, since they're already adapted to these extreme conditions. Bioscope Technologies emerged as a spin-off from the e-waste recycling company N2S, established to bring bioleaching technology to market. The company specializes in recovering valuable metals from printed circuit boards or PCBs. PCBs are flat boards made of non-conductive material with copper pathways that mechanically support and electrically connect electronic components in devices. PCBs contain valuable metals such as copper, gold, silver, nickel, zinc, and palladium that could contribute to metal demand if they were extracted at scale. Currently, Bioscope has gold extraction underway and is developing processes to extract palladium and platinum. They're also capable of recovering significant quantities of copper from PCBs. Bioscope has filed patents for its innovative bioleaching and biorefining techniques and operates state-of-the-art facilities, including a PCB shredding system capable of processing 5 metric tons of PCBs daily. The company approach is designed to minimize emissions without the need for carbon offsets. As of 2024, Bioscope operates 4 state-of-the-art recovery and processing facilities across the UK, addressing a critical need given that under 40% of the UK's electronic waste is recycled domestically. Bioscope Technologies is working with Coventry University through a Knowledge Transfer Partnership, or KTP, to accelerate the development of its bioleaching technology. KTPs are a UK-wide programme that connects businesses with academic institutions, helping them apply research and innovation to real-world challenges. Each partnership includes a graduate known as the KTP Associate, who works on the ground to deliver a specific project, in this case making e-waste recovery cleaner and more efficient. Funded by Innovate UK and supported by a dedicated advisor, the KTP gives Bioscope access to cutting-edge academic expertise while advancing solutions that support a more circular economy. A recent study suggests that bioleaching methods have the potential to be up to 2 times cheaper than hydrometallurgy and 4 times cheaper than pyrometallurgy. Apart from cost benefits, bioleaching offers a low-emission, simpler and safer alternative to traditional methods, and is even suitable for regions without established recycling infrastructure. As mentioned, it's scaling the technology that will likely pose the greatest challenge, as well as better understanding and optimizing the process for quicker recovery and better selectivity towards particular metals. That being said, the technology is attracting increasing attention from major tech companies, particularly data center operators and cloud providers, who are seeking sustainable end-of-life solutions for their hardware. As one industry expert notes, they all want to discuss the merits of building plants specifically for their own use, highlighting the growing demand for dedicated closed-loop recycling systems tailored to large-scale electronic infrastructure. I think it's interesting how, more and more, we're seeing bio-based solutions in circular and sustainable innovation. In a recent video, I explored how algae can be used across a wide range of applications, from biofuels to water treatment and animal feed. And mycelium keeps making headlines as a sustainable material for everything from meat alternatives to packaging and even leather substitutes. Really, this trend shouldn't be a surprise. Nature has always operated in closed loops where nothing is wasted and everything gets reused. If this topic sparked your interest, feel free to check out my video on algae. It should be linked here somewhere on the screen. As always, I'm Luke, and this was The Upshift.